welcome to today's Technical Sciences lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Great job. Today we are doing a very exciting lesson or topic, a visual one. We are looking at our knowledge area for the day is wave, sound, and light. More specifically, as I say, we are looking at light. That's why we are saying that it's an exciting lesson or an exciting, interesting topic that we are looking at, a visual topic where we are looking at how do we actually see things and how does light behave. All right, our subtopic for today, we are going to be focusing on reflection and refraction. Right, so let's go right into it. Okay, for today, our lesson objective is that we must be able to, by the end of the lesson, define what reflection is. We must be able to state and understand the laws of reflection, define refraction, also define and understand what critical angle is, define and understand the total internal reflection, and also define and explain dispersion of white light, differentiate between concave and convex lenses, and also draw the transmission of light through a concave and a convex lens. So those are the objectives for the lesson for today. The knowledge that we are expected to come to the lesson with, things that we have learned previously. You would remember that in grade 11 we looked at waves, so we should be able to define a wave. And also in grade 11 we looked at reflection in the form of sound, reflection of a sound wave. You remember that in grade 11, so we should be able to define and have a little bit of understanding as to what do we mean by something being reflected. So we should be able also to draw just a simple diagram showing the reflection of a sound wave, right? We should be able to explain or even define what frequency is, or also explain or even define what a wavelength is, as we looked at them during our grade or last year in grade 11, right? So to just assess some of these things and check whether people still remember them, I'll just simply ask the following question. Can you define a wave? Can you define the term reflection? Can you draw and labeled a labeled diagram showing the reflection of a sound? And can you tell us what is meant by the term frequency? And also please define the term wavelength. And if you can do those things, the answers to the questions should be as follows. You say a wave is a disturbance that transfers energy through matter or space. Okay, then the next answer to the question will say the change in direction of a wave upon striking the interface between two materials. That will be the definition of reflection. The change in direction of a wave upon striking the interface between two materials. Okay, and a simple diagram, I decided let's use this diagram because this is particularly the diagram that was used last year, especially from your textbook in grade 11, a diagram that was indicating how sound can be reflected or reflected on a certain object, right? If you remember last year, there was sort of this experiment that you could do to say take a stopwatch, a ticking watch, in fact, whether it's stopwatch or an analog watch, as long as it ticks, and then also create these cardboard and have soft wood that is in between and then listen on the other side. One of the learners will listen on the other side while the other one is holding the stopwatch, and you remember that sound was transmitted there or was reflected there. And then we said the reason why the other one can hear the sound is because sound is being reflected, bouncing off. You would also remember we were even speaking of things like echoes or how dolphins hunt, right? Or using echolocation, including birds. These are the things we spoke of while we were in grade 11. Okay, the next answer will be the definition of frequency. We will say frequency is the number of waves that pass a fixed point in 1 second. Again, and then wavelength is the distance between two successive points that are in phase. Those are the definitions that we looked at in details last year, and those are the things that we should bring in as we embark on this journey of learning about light as a wave for now. Okay, so the terminology that we will encounter for today and things that we need to know. Well, reflection, even though we already know it from last year, the change in the direction of the wave upon striking the interface between the two materials. This year, we should also know refraction, and we'll define refraction as the bending of light when it passes from one medium to another. Critical angle is the angle of incidence in the optical dense medium, for which the angle of refraction is 90 degrees. Total internal reflection will be when the angle of incidence is greater than the critical angle. The ray of light reflects back into the original medium. We'll also discuss what this means, and we'll be looking at diagrams then. And then we also look at dispersion of white light, right? Dispersion of white light as a phenomenon whereby white light spreads. White light will be spreading into its component colors. That's what we're also going to look at there. We'll also look at convex lens, and we're going to look at convex lens as a lens that is thicker in the middle than in the edges, and the concave lens, we want to explain or identify it as a lens that is thinner in the middle and then also thicker on the edges. And then other terminology that we need to know while we are working with lenses are things such as the principal axis, which is a straight line perpendicular to the surface of the lens and passes through the optic axis. And then we have optic axis, the central line that passes through the center of curvature of the lens surface, and the focal length, the distance between the focal point and the center of the lens, and then the focal point, which would be the point in space where parallel light ray meets after passing through the lens. That will be the focal point, where they meet or even where they appear to have been coming from. We'll be discussing all of that in details when we look at those lenses. Okay, without wasting any time, because there's a lot that we must cover for today, let's go right into it, and let's look at reflection. Okay, so grade 12 reflection in essence, reflection explains how we see things. Okay, how is it that I'm able to see you? How is it that I'm able to see things that are in front of me? And it's said that light bounces off, light rays go in and they bounce off the object, an object that is opaque. If you remember, an object that is opaque, that does not allow light to pass through it. Right? So if you have an object that is, or a material that is opaque, that does not allow light to pass through it, this material will then reflect light back to us, or back to the observer. Let's put it like that. Okay, what is this reflection? Well, according to the examination guideline, it is defined as the change in direction of a wave upon striking the interface between the two materials. So when a light ray enters or a light ray approaches a certain material, the light ray will then bounce off and changes its direction. Okay, it's not going to go through. Why? Because we are talking of an object again that is what? That is opaque here. Okay, we are talking an object that does not allow light to go through it. Okay, so if you have such an object or such a material, this material will then change the direction of light as light comes in here. So the way we investigate this grade 12 is we look at one light ray, because if you think about it, maybe if you had a source of light like the sun here, the sun will have thousands and thousands and thousands of light rays that are being emitted from the sun. So we only take one of these light rays and we draw them using a line with an arrow to just indicate that this is a light ray. Okay, and then this light ray, we say, what if we only look at one light ray and it was to approach this interface or this material here that does not allow light to pass through? What will happen to the light ray? And we find that the light ray will come in, approach, and it will hit the interface between the two materials, and it will change the direction such that it is bouncing almost as if it bounces back. So it hits the interface and then it changes direction as if it was bouncing back. Okay, however, it does not just change the direction anyhow. Okay, there are certain laws that this light ray is going to follow as it changes the direction, and these laws, we call them as the laws of reflection. Okay, right? Number one, before all of that must happen, we must make sure that the incident ray, the reflected ray, and the normal all lie in the same plane. Now, question will be, what is the incident ray, what is the reflected ray, and what is the normal? Well, let's go back to say here. Here we said we have a light ray that comes from some source, light source. Let's say the sun was here, right? We have a ray that comes from some source, and that ray is going to or approaching a certain object that is opaque. That one ray that we said we are going to consider is called the incident ray, as it is incident, okay? That one ray, we call it the incident ray, the ray that is coming in, okay? Then it then touches the interface between the two materials, and then it changes direction, as the definition says. The ray that now is coming out or comes from the material itself after it had bounced back, the ray, we now name it the reflected ray, because that ray is being reflected. It is being reflected by the opaque material. So we call it the reflected ray. Okay. Now, in between the two rays, there is an imaginary line that we usually draw. Okay. This imaginary line is drawn perpendicular to the surface of the material itself. So then if it is perpendicular, we are going to call it what? The normal. It's called the normal because it is perpendicular to the surface. You would remember that at some point we were talking about forces, and we discussed the force, normal force. And we said normal force is the force that is perpendicular to the surface. It is applied by the surface perpendicular to the surface. Hence it was called the normal force. This is also called normal because it will always be perpendicular to the surface, but it is an imaginary line that does not necessarily exist like the light rays. Light rays do exist, but this one does not exist. It's imaginary. We call it the normal. Okay, this line is used to measure angles, right? An angle from this line to the incident ray, and also an angle from also this line to the reflected ray. Okay, so when these angles have been measured, what do we call them? The angle that is measured from the normal to the incident ray is called the angle of incidence. Okay, it is the angle measured from the normal line that we drew here, an imaginary line that sort of separates the incident ray and the reflected ray. It is we measure from that, from the normal to the incident ray. That angle is called the angle of incidence. While the angle that is measured from the normal to the reflected ray, that angle is called the what? The angle of reflection. So itself, these things, they just answer themselves, or they say themselves. It's angle of incidence because it is measured from the normal to the incident ray. It's angle of reflection because it is measured from the normal to the reflected ray. Be careful not to make a mistake. Again, I emphasize, the angles are measured from the normal. They are never measured from the surface or from the material. This measuring the angle here will be completely incorrect. You never measure angles from the surface of the material to the incident ray and then call it the angle of incidence. No, the angles are always measured from the normal. It's important to remember that when maybe you have to draw a diagram and represent this thing. When you do that, to indicate your angle of incidence and your angle of reflection, they must be drawn from the normal or measured from the normal. Back to the laws that we were discussing. We're saying the first thing is that the incident ray, this ray here, the reflected ray, this ray, and the normal must all lie in the same plane, right? You remember again, last year in grade 11, we talked about planes where we were looking at coplanar vectors, right? We know a plane as, and we look at it as a face, sort of a face, or as a face to say, when we are in the same face, we say we are in the same plane. So all of these rays and the normal must lie in the same plane, okay? And then if that is going to happen, the angle of incidence will always be equal to the angle of reflection. The angle of incidence will always be equal to the angle of reflection, as it is again shown here. Always always equal. Is equal talks about these two angles. Angle of incidence is equal to the angle of reflection. That's a law. So you are never going to have an incident ray maybe being incident at an angle of 50 degrees, and then now you find this one being reflected at an angle of 70 degrees. That would be completely incorrect. Okay, that is not going to happen. Reflection follows certain laws, and one of the laws is that the angle of incident will always be equal to the angle of reflection. So if it was 50 degrees here, it is also going to be 50 degrees as the angle of reflection. Okay, so here's an advice that I usually give to learners grade 12 to say, how then do you write this law of reflection? Says a question is asked, give the law of reflection. Okay, the advice I always give to learners is that do not write one of these laws. Don't choose between this one and this one and say I'm just going to write one. Write all of them. Combine these two laws and turn them into one law. They are called the laws of reflection, but you can just combine them and turn them into one law. How? Right? They say state the law of reflection. You say the angle of incidence is always equal to the angle of reflection. Right? Then you say the incident ray, the refracted ray, and the normal all lie in the same plane. You have done exceptionally well if you do it like that. Just write both of them always if you are answering a question where they ask you to state the law of reflection, because the question could say state the law of reflection instead of the laws of reflection, and then you end up thinking maybe you will choose one between the two. Just you write both of them. That's my advice to you. You are just making sure there that you are covering your back there just in case there are debate as to which one should be marked, which one should not be marked. Put both of them. You'll be covered that way. So all in all, that's what happens during reflection, and that's the most important thing for you to say. Understand that in reflection you are going to have the incident ray, you are going to have the reflected ray, and you are going to have the normal. And then you are going to have the angle of incidence, and then you are going to have the angle of refraction. This reflection, this is what is important for you to understand, and also understand the definition of the two things when it comes to reflection. Grade 12. Be careful every time when you draw. You must always indicate and label these rays. Drawing the reflection only is not enough. So you must always label incident ray, reflected ray, angle of reflection, angle of incident. Label the normal, and then also label your material. If you were told what material you are working with, okay, it might be a mirror or any other material that is opaque and does not allow light to pass through. Okay, so that's it. When it comes to reflection that we are going to look at, we're not going to go any deeper there. That's what I want you to understand when it comes to reflection. So let's move on and try and look at the next concept that where we will take us some time, and then we're going to discuss it in details. The next concept will be refraction now. Okay, so what is the reflection? That's when light changes direction upon striking a certain interface of a material. Okay, so what about refraction? Well, not all objects are going to be opaque. Not all objects are going to be opaque. Some objects are transparent. Okay, so what happens when we talk of transparent object? Well, we know that transparent objects are going to what? Allow light to pass through. Okay, not all the light in a transparent object will be reflected. Most light in a transparent object can pass through. This is the reason why we can see things when they are over the transparent object. You put a clear plastic bag in front of your eyes there, you can see beyond that plastic bag. Okay, you can look through the window. The window is a material itself, but you can't look through a wall. A wall will always reflect light. Okay, it's opaque, it does not allow light to pass through. However, a window is transparent, so the window will allow light to pass through. But how does light pass through in the window? Light passes through such that it is refracted on the window or any other transparent object or any other object that transmits or allow light to pass through. It passes through such that it is refracted. And what do we mean by refracted? Well, refraction is defined as the bending of light when it passes from one medium to another. So when light enters a medium like glass, okay, it will go through, you will see through it. However, it is not going to go through straight. Instead, it will be refracted, okay? It will bend, okay? It will bend as it passes from one medium to another. As this diagram shows here, you have light that is coming from one medium to another medium. Say, for example, we say this medium that it comes from is air, and it is going to a medium, maybe let's say this medium is glass, or it could be water, or any other medium, okay? What refraction tells us is that this light is not going to maintain a straight line, because if you look at the diagram here, a straight line would have been something like this, right? However, the light did not take this path. Immediately when the light entered here, the light bent, it changed direction, okay? It changed direction, but not by going back to the same medium as in a case of reflection. In this time, it did go through this material, which is glass. It did go through. However, it did not maintain the same direction. Instead, it changed direction a little bit by bending. So it was bending here, showing that something is happening, and that thing we call it what? Refraction. It is refraction. The light bending as it passes from one medium to another. Okay, so when we are having refraction, we are also going to have incident ray, because we are still talking of what? Of light. So the ray that is going to be going in, we call it an incident ray. And then the ray that bends, or the ray that changes direction as it enters the medium, that ray is called the refracted ray. It is called the refracted ray because that ray is refracted. That ray is bent. It changes, or it bends as it enters a different medium. So you have incident ray and you have refracted ray. In reflection, you had incident ray and reflected ray. So you must be able to differentiate between the two, okay? And always remember, the other one is reflection, the other one is refraction. So here we have incident ray, and we also have refracted ray. Okay, we also have this imaginary line here, which is perpendicular to the surface of the boundary between the two mediums, or the two media, okay? And that line is called what? The normal. That line is called the normal, okay? Again, from that line, that's where we measure our angles, and the angle from the normal to the incident ray, and also the angle from the normal to the refracted ray. You would remember that when we were talking about reflection, we said these two angles are always equal. So if we say theta I, which can stand for angle of incident, is equals to theta R, which is what? The angle of reflection here. So this is always the case for reflection. So is it always the case as well for refraction? That is not the case for refraction. Okay, so we have the angle from the normal to the incident. We can call it theta I as well. It is called the angle of incidence again. Okay, then here we can call this one theta R. Okay, again, this one is the angle of refraction. Is theta I equals to theta R here? And the answer to the question is no. In this case, we are not going to have the angle of incidence being equals to the angle of refraction, okay? The angle of refraction will always change from what the angle of incidence was, okay? And it will change depending on the material that the light is going to, okay? So the light will bend, and when the light bends, that means that this angle changes. It cannot be the same angle, because if it maintained a straight line, this angle would have been equal to this angle, right? Vertically opposite angle according to math there. But now, since it bends a little bit, we cannot say these are vertically opposite angles. This one becomes a little bit small. Are we together? So in this case, this refraction, the angle is a little bit smaller. But we are also not saying the angle in refraction, the angle of refraction will always be small. It will depend from which medium the light is going and is coming from, and to which medium is it going. Okay, that it will depend, and that's what will determine whether the light ray will bend towards decreasing the angle or bend away, increasing the angle. Okay, it depends on what? Okay, this is going to depend on something we called optical density. It's going to depend on something we call optical density. So materials have different optical densities, grade 12, okay? We have materials that are more optical denser, and we also have materials that are less optical denser, okay? So we don't have enough time to look at all material and know that this material will be more optical dense, this material will be less optical dense. So we'll just explain it in general to say how I want you to think of a more optical dense medium. I want you to think of a more optical dense medium as a medium where it will be difficult for light to pass through as compared to the previous medium. Okay, I want you to think of a light, like for example, do you think it will be difficult for light to go through air? And if you agree with me there, you should say no, it shouldn't be that difficult. If we compare to light going into water, for example, okay, when you look at water and air, the particles that make up air, if you remember the particle model of matter from grade 8, the particles that make up air, we say that those ones, they are just loosely bound. The particles are all over the place, all right? As compared to water, which is liquid, they are close to each other. They might be loosely bound, but they are more closer to each other than those of air. If this was air and this was water, the particles here are more closer to each other on water as compared to air. So if the particles are loosely bound and they are all over the place on air, that should make it easy for anything that travels through them to go or to travel. So the light will travel easy through these particles as compared to when the light wants to travel through the particles of water. It will make it difficult. So then it means that more water must be more dense than air. Air will be less dense. Okay? Now, if light comes in from air to water, then it means light is coming from a less dense material and it is going to a more dense material. Okay? So let's think about glass. Glass should be almost similar to water if we were to compare it to air. When you compare to air, particles all over the place, glass should have particles that are relatively close to each other, maybe even closer than water, okay, right? So if light wants to pass through light or through glass, it should have difficulties as compared to when it was trying to pass through air. I hope you understand me when I'm trying to explain this issue of optical density, right? When light passes through air, should pass relatively easy when we compare to light that wants to pass through what? Through a glass. So when you think light it will have difficulty passing through that material compared to where it was coming from, then you would say that material is more optically dense as compared to the previous material. The materials that will be used for examination purposes, grade 12, will be easy. It will be easy for you to see. Usually it's air, glass, air, water, and air with maybe diamond. It's usually easier for you to see that this one will be optically less dense and this one will be optically more dense. It should be simple to determine that. As long as you understand this, what do we mean by optical density? Okay, so remember, we want to find out how will the angle behave. Will the angle be greater than? Will the angle be smaller than? Okay, so when light moves from an optically or less dense medium, or sometimes called an optically rare medium, I just like to use it's less dense, okay, to an optical more dense medium. This one is more dense, okay? It's glass versus air. Air is less dense, glass has to be more dense. So when light moves from an optically less dense medium to an optically more dense medium, in this case, light will bend towards the normal. We say the light bends towards the normal or closer to the normal, meaning that theta r will be less than theta I. So theta r will decrease in that case, okay? Theta r will decrease in that case. But we also have to look at what is actually decreasing this theta r, or what decreases this angle. Why does it bend towards the normal? What is happening with light? Okay, you would remember that light in a vacuum from again last year travels at a speed of 3 times 10 to the power 8 meters per second. Okay, it travels at a relatively or almost the same speed in air. So for simplicity, let's assume it travels at that speed also in air. And light approaches, and then light enters a different medium. A medium where there are more particles, if you remember. This was the medium where there were less particles. Now it enters the medium where there are more particles, a more optical dense medium, a medium with a high density, okay? What is going to happen to speed or to the light itself, okay? An example I would ask you is, imagine you were running and you are running on a free ground, there is nothing disturbing you, and then immediately you enter a place where there is water. Now there is water. How is your speed going to be affected as you run there? Because we were running on a free ground, it was just air, particles. It was easier for you to run, right? Immediately you enter the water, running is going to be difficult. The speed in which you were running, I expect is going to decrease. I hope you agree with me. You should be agreeing with me then. The same thing happens with light here, grade 12. As light was moving in air, which was a rare medium or an optical less dense medium, right? It was moving with ease. Immediately it enters the other medium, which is glass, which is more dense, more particle. The speed of light decreases. The speed of light here is going to decrease. This decrease in the speed of light is what causes this light to change direction. This is what causes this light to bend. It's the change in the speed of light, okay? Because light was moving from an optically rare medium or an optical less dense medium to an optical more dense medium. As it entered the optical more dense medium, its speed decreases, and this decrease in speed caused it to bend, and it will bend towards the normal, okay? So we can now make a conclusion to say, whenever light is traveling from an optically less dense medium to an optically more dense medium, the expectation is that the light ray will bend towards the normal. Very, very important, grade 12. I will repeat that. When light travels from an optically less dense medium to an optically more dense medium, the light ray will bend towards the normal. What is happening there? The speed of light is decreasing as the light ray enters an optically more dense medium. It will affect the speed of the light, causing it to bend towards the normal, okay? But are we going to be having light only moving from an optically more dense medium to an optically, for an optical less dense medium such as air to an optical more dense medium such as light? Not always. But as you can see here, this is what we are talking about. Light ray coming in here. This will be your incident. This will be your incident ray coming in here. And this will be your refracted ray here bending. As you can see here, this is what I was trying to show you here. It is not maintaining this original path. Instead, it bends towards, as you can see here. If you compare these two angles, this one is relatively bigger than this one. So theta r is bigger than theta I mean, is bigger than theta r in this case. Why? Because when this light ray entered the glass, which was more optical dense, or which was denser, and this one was rarer, okay? When light entered the glass which was denser, its speed decreased. So here we had a what? A decrease in the speed of light. So it is no longer moving with that speed of 3 times 10 to the power 8 meters per second. It decreased drastically, causing this to do what? Causing the light ray to bend towards the normal. Again, I say, whenever light travels from an optically rarer medium to an optically denser medium, the light ray will bend towards the normal. Very, very important for you to remember. As you can see here, it is written, light slows down. Light slows down. Another way of saying the speed decreases then. Okay? So then what happens if we change? Let's make light to be incident from water. Let's say light is incident from water and it is going to air. What do we think is going to happen there if light is incident from water and it is traveling towards air? If we look at water and compare it to air, we should say that, well, water should be the one that is what? That is denser. What about air? Air should be rarer. It should be simple for light to pass through air. The particles are spread apart, while the particles in water are relatively closer if we compare it to air, of course. Okay, so what happens there? You have the incident ray. The ray is incident now from water. Okay, you have the incident ray. You have your normal, which is the perpendicular line, imaginary line. Right. Is the light going to maintain the same path that it had while it was moving towards the different medium? The answer to the question is no, grade 12. It's not going to maintain the same path. Are we together? Instead, it's going to bend. It will be refracted. It will be refracted. Okay? Or we should write here, refracted ray. The light ray will be refracted. Okay? Now, how will it be refracted? Is it also going to bend towards the normal? And the answer again there is no. This time around, it will not bend towards the normal. Why is the light not bending towards the normal? When light is moving from an optically denser medium to an optically rarer medium, or an optically more dense medium to an optically less dense medium, the light is going to gain speed, right? Again, let's now look at that example that we had in the opposite way. Now, let's say you are starting to run in water, and then all of a sudden you encounter dry land. Your running is going to change drastically. And how will it change? You are going to gain speed. You will run faster than you were running in water, because in water, the particles were closer to each other, kind of limiting how fast you were running. But then when you get to air, the particles are spread apart. You can run even faster. The same thing happens, almost the same thing happens with the light as it enters from one medium to another. If the medium it comes from was more dense, then the light was moving slow. It means the light is not moving at a speed of 3 times 10 to the power 3 times 10 to the power 8 meters per second. There, it's moving at a speed that is very, very low because of the density of the medium itself. And when the light now enters a different medium such as air, the light is going to gain speed. So here we're going to say the speed increases here. The speed increases. While there we were having a decrease in speed. Here the speed increases. If the speed increases here, then this means that this light ray is just going to start shooting, moving faster. And if that happens, then the light ray will bend away from the normal. The light ray will bend away from the normal, creating an angle of refraction that is bigger than the angle of incident or incidence. Okay, it will create an angle theta r, which is bigger than theta I. So theta I here is always going to be smaller than theta r if the light is coming from an optically dense medium to an optically rarer medium. Okay, then the light ray will bend away from the normal. But if it is coming from an optically rarer medium to an optically denser medium, the light ray always bends towards the normal. Very, very important things to remember when we are talking about refraction then. depending of light as it enters from one medium to another grade 12. Okay, very, very important there. Right. So what I want us to do now, I want us to investigate, okay, more this part where we say the light ray bends away from the normal, because that means more can be done here if we were to investigate this. Okay. So if we are having a light ray that is coming incident from water, okay, let's say this here is water and goes to air. So it comes from an optical dense medium to an optical rarer medium. Okay, we know now that the light ray is going to do what? Bend away from the normal, creating a refraction or an angle of refraction that is bigger than the angle of incidence, right? Okay, what happens? What do you think is going to happen if I increase this angle? Okay, what happens if I increase theta I, the incident angle or the angle of incidence? Okay, what do you think is going to happen to the refracted ray? I hope you're with me when you say the refracted ray will bend further away from the normal. So if I now incident it at an angle like this, it will refract it more at an angle like this. Okay, what about if I increase it even further? You increase it further at some angle, at some point, this refracted ray will be refracted such that it lies on the boundary. Hope that you agree with me. You see where I'm going here. There must be an angle where I have incident the light ray such that the refracted ray is lying at a boundary between the two mediums. Okay, that is a very, very important thing, because that is a very, very important point that will be there. This is what I'm talking about. The incident ray now is such that the refracted ray is lying along the boundary between the two mediums or the two media. Okay, what is happening here? Here we are no longer having the angle of incident, or we say the angle of incident is now equal to something else. Okay, we are having a new concept altogether. We are now having a critical angle. At this point, it's critical. I always say when they say a person is in a critical condition in hospital, that means this person, we are not sure what's going to happen. This person might make it, this person might not make it. Anything happens, this person does not make it, or anything happens, this person recovers well. Just an example that I always think about, because the word critical is usually used in hospital where they say it's in a critical condition. This is where we are with our incident rate. We are in a critical condition. If you keep on increasing, because remember we were increasing the incident angle. We increased it, it went further away. We increased it, it went further away, if you remember. Keep on increasing, now it is at the boundary, or it's lying at the boundary. Now, this angle, we are no longer calling it the angle of incident. We're now calling it the what? The critical angle. Okay? Critical angles are not the same, right? As a light rays do not refract the same in material. It depends on their refractive indexes, okay? Which is something that we don't need to be talking too much about, but it depends on the refractive index of a material. So even the critical angles of materials are not the same. Okay, but we don't need to dwell too much on that. What we want to know is that each and every material that allows light to pass through will have a critical angle. It will have an angle such that if you incident a light in that angle, the refracted ray will lie on the boundary between the two media. Okay, like this. What do we how do we define this critical angle? We say this critical angle is the angle of incident. So the critical angle is the angle of incident, but it is the angle of incident in the optical tensor medium for which the angle of refraction is equal to 90 degrees. It is the angle in the optical tensor medium for which the angle of refraction is equal to what? 90 degrees. Okay, excuse me there. So that tells us that for us to have a critical angle, there are conditions. Right? It means there are conditions for us to talk of a critical angle. Okay? All right? What's the most important condition there? Most important condition is that light must be coming from, light moves from optically dense medium or denser medium. Okay, light must be coming from an optically denser medium. So this critical angle issue is not going to occur, or we won't be able to observe it if the light is coming from an optically rarer medium. The light must be coming from an optical dense medium. Okay, and then condition number 2 is that the refracted ray, or the angle of refraction be equals to 90 degrees. Well, this is just going to happen on its own. If you are at the critical angle, the angle of refraction will just be 90 degrees. It will happen on its own. But the most important condition is that now we have reached an angle where we are at critical. It is now refracted such that it creates an angle of 90 degrees with a normal. You continue doing this, you are forming something different. And what are you forming there? You are giving us a new concept altogether. Remember, all these concepts are coming from what? Are coming from refraction. We're just talking about light that bends as it enters one medium from another, remember? But then you kept on increasing the angle of incidence in the optical denser medium. You notice that the refracted ray kept on bending further away from the normal, At some point, it was lying on the boundary. And now we said we are at a critical angle, as this case is showing us. You were here, incident angle, the ray was refracted. You kept on increasing this, the ray was further refracted. You kept on increasing, the ray was further refracted. At some point, you increased and you reached this angle. The ray was refracted such that it creates an angle of what? Of 90 degrees. You are now at a critical angle here. You increase this angle even further, you change the concept altogether. And what is going to happen? The light ray is no longer going to be refracted if you do that. The light will not go through the medium. Okay? It's not going to reach the other medium. We go back to the first concept that we looked at. Here you are going to have what? Reflection. Sorry, you are going to have reflection. These words, refraction, reflection. You are going to have reflection. But what type of reflection are you having? Remember, this reflection is happening within the medium, internally or inside the medium from which the light is coming in. So we call it total internal inside reflection. It's total internal reflection that is going to occur. Total internal reflection is going to occur if you keep on increasing the incident angle and you reach an angle that is greater than the critical angle. Once you reach an angle that is greater than the critical angle, total internal reflection is going to occur. In that case, grade 12. How do we define total internal reflection? According to the exam guideline, we say when the angle of incidence is greater than the critical angle. When the angle of incidence is greater than the critical angle, the ray of light will reflect back into the original medium. When we expected it to go through, because we were looking at a transparent object that allows light to pass through, we were looking for it to go through but bend. But now you have increased the incident angle such that it is now greater than the critical angle. Then the ray of light does not go through. Instead, it reflects back into the original medium. The laws of reflection all come back. Yet again, the incident ray, the reflected ray, and the normal all lie in the same plane, and the angle of incidence is equal to the angle of reflection. All of those laws are going to apply again. This becomes the incident ray yet again, and this becomes the reflected ray yet again. While here it was the refracted ray. Okay, so you have changed this thing altogether. This will always be incident. This will always be incident. So it was incident refracted, it was incident refracted, but then you had an angle that was greater than the critical angle. It totally and internally reflected back into the medium, and it changed into what? a reflected ray. So that's what is a total internal reflection, okay? Just in a nutshell there, right? As we say there, that the laws of reflection are going to take place. So from what we've said, we can then conclude again that total internal reflections have conditions, two most important conditions that must be met again, right? Again, we say light must be traveling from a more optical dense medium to a less optical dense medium, because again, you're not going to have a critical angle without that. It was even a condition for critical angle. It becomes the conditions again for total internal reflection. Light must be traveling from a more optical dense medium to a less optical dense medium, or from a denser medium to a rarer medium, okay? And condition number 2 there, very important, the angle of incidence must be greater than the critical angle. Make sure that the angle of incidence is greater than the critical angle. It must be bigger than the critical angle. Then in that case, you are going to have total internal reflection. Okay, so we'll just go through a little bit some examples where total internal reflection is used, or where you find total internal reflection being used there, right? The first one is total internal reflection is used in optical fibers, which these are tools or conduction that are used for what? For communication. How to get, right? These are used for communication, optical fibers. For mostly nowadays that are used for internet. You know that internet will say we have fiber and all of those things. The optical fibers are used there. Great talk. Okay. Another example there will be binoculars. Binoculars use the concept of total internal reflection for it to be able to what? To show you whatever you are trying to look at. Periscopes, okay? Periscopes also are used, or they use the concept of total internal reflection, and also fish-eye lenses. They also use the concept of total internal reflection. There are a lot of examples that use total internal reflection. These are just a few that I took, and I wanted to show you that these are real life examples where you would find total internal reflection occurring there. So it's just important for you to know the examples where you can find total internal reflection, as it shows them in your optical fiber. We don't have, unfortunate, time for us to go through each and every one as to how the total internal reflection occurs there. But it's important for you to understand that total internal reflection occurs in all of those materials. Okay. Right. Now this takes us to another concept, okay, that we want to look at great off. I now want to look at the dispersion of white light. What is dispersion of white light? Well, dispersion of white light is the phenomenon whereby light breaks up into its component colors, okay? So the question is, why is it that we are able to see all these colors, the red, the blue, while we just use the same light for all of them? It is because white light can break up and cause all of these colors. As you can see, these beautiful colors, I'm sure it reminds you of the rainbow, okay? If you can see them, these are rainbow colors, okay? These colors, they come about because they have been what? They have been released, or they've been broken up from white light, okay? They broke out from white light, so they break up there and into their component colors, okay? So white light, and how does all of this happen? Okay, so you pay attention there, great talk. So white light comes in. When white light is coming in, within white light itself, all colors are there, all of them, okay? The major ones are the ones that have been listed here, okay? But within white light, all colors are there. So white light carries all colors, okay? So while white light is moving here, would say that white light is moving at the speed of 3 times 10 to the power of 8 meters per second, yet again, because it's relatively close, okay? So let's say, assume for simplicity, it's moving at that speed. All these colors are moving with the same speed in white light when white light is in air, okay? Right. Now, all of these colors here, they have different frequency. They have different frequency. Grade 12, okay? It's important for you to understand. Now, you follow me, okay? While they are here, they have different frequency. Red will have a different frequency than violet. By the way, the lights are called red, orange, yellow, green, blue, indigo, and violet. Expectation is that everyone knows this because everyone must know colors of the rainbow from primary, okay? There's red, orange, yellow, green, blue, indigo, and violet. All these lights, they have different frequencies. While they are moving within white light, okay? They have the same speed though. The reason why we can't see them before they enter any prism is because they are moving at the same speed. Grade 12, okay? So while they are here, they are moving at the same speed with different frequencies, but the speed is the same. That's why we can't see. All we see is white color. They are white, okay? Now, they enter a glass prism. We've spoken about this. We are having light entering from one medium to another medium. We're having light entering from an optically rarer medium, and it is entering a dense medium, okay? Right? It's entering a denser medium. What is going to happen to light as it enters a denser medium? It is going to be refracted, okay? And why is light being refracted when it enters a denser medium? It is refracted because the speed of light changes as it enters here. Very important, grade 12. The speed of light changes. Okay? As we say here, white light changes speed as it enters a prism. So when it enters the prism, the speed changes. What's going to happen? The speed is going to slow down, to decrease from the 3 times 10 to the power 8 meters per second to a number that is less. Don't know what the number is, but to a number that is less. Okay? But now, the speed is not going to change the same. So they are not going to have now the same speed while when they enter the prism. Okay? They are going to change their speed differently. Some of the colors are going to be faster than other colors. Okay? And the reason why some are faster than the other colors is because they have different frequencies. Their different frequencies will affect how their speed changes. Now, because of their different frequencies, you'll find some being fast, like red. Red will be the what? Will be the faster lighter here. It's faster than a faster color, I mean. It's faster than all of these colors. While violet is the slower color here, and violet is very, very slow. Okay? So, because of the frequency, the speed is going to change such that red is going to be extremely fast, faster than the other colors, such as violet, okay? So this is going to cause violet to be refracted the most. It will be refracted the most. You'd remember that if we were to draw our normal here, which is a perpendicular line, it would be something like this. Our normal here, it will be something like this, grade 12. So you can see that the violet is bending closer to the normal than the red. Why? Because it is slow white, or it's the slowest. So it gets refracted the most. While red gets refracted, the least. So it gets refracted the least because it is faster. Why it's faster? It is because of its frequency. Okay, right. So as we say here, red is the fastest. Okay, it has the longest wavelength, while violet is the slowest. It has the highest frequency. Okay, so because of the highest frequency, violet is going to be the slowest. Okay, because of the longest wavelength, or red, is going to be the fastest, or is going to be extremely fast. Okay. Now, sometimes we find that people struggle to remember these colors when they don't see them. So, one way of remembering these colors, grade 12, is just to have sort of this mnemonic that I usually use with learners. I say, just say this is Roy G. Beef. Okay? Always when you talk of dispersion of white light, just say Roy G. Beef. Okay? Roy G. Beef is one way you can always remember all 7 colors and remember them easy. Okay? Roy G. Beef, I think it should be obvious now. R stands for red, O stands for orange, Y stands for yellow, G green, B blue, I indigo, and V violet. Roy G. Beef. Okay? Then after you write your Roy G. Beef, I just want you to just quickly have your arrows here where you write increase in frequency. Okay? And then here, the arrow where you write increase in wavelength. I'll use a symbol for wavelength because of space there. So when we go from violet towards red, we are increasing wavelength. Hence, we are saying red has the longest wavelength out of all these 7 colors. When we go from red to violet, the frequency increases. That's why we said violet has the what? The highest frequency. Okay? You would remember the relationship between frequency and wavelength is that of inverse proportion. Okay, is that of inverse proportion. Okay, so if you remember the formula that we looked at last year, so the relationship between wavelength and frequency is inversely proportional. Where there is high wavelength or where there is longer wavelength, there is actually a low low frequency. Okay, where there is longer wavelength, there is low frequency. Where there is high frequency, there is shorter wavelength. Okay, high frequency here, wavelength is short. Okay, but if we remember the relationship here, if we were to keep the frequency constant, because as much as their frequency, their individual frequency is not the same, okay? As much as their individual frequency is not the same. When light bends through the prism, the frequency does not change. It remains the same. The only thing that changes is what? Is the speed of light. The speed of light changes. And the change in the speed of light also affects the what? Also affects the wavelength of these colors. Okay? Because the speed and the wavelength will also be what? Affected there. Or either or to say the wavelength is the one that actually affects the speed, making it to what? To be slower or even faster. But the truth of the matter is that the one that will be the fastest there is red, the one slowest is violet. Okay? And red being the fastest is going to be refracted the least, while the violet will be refracted the most. So it's very important for you to understand this thing and understand it in terms of the frequency there, understand it in terms of the speed decreasing. Okay? So that's dispersion of white light. That's how we end up seeing all these light. So these lights are actually coming from white light. So that tells us that white light carries all these light or type of light within the light itself. So all colors, all colors that are within the light itself, white light. So what is important here, grade 12, is that you remember to be able to do what? To define dispersion of white light as the phenomenon whereby white light breaks up into its component colors. Okay? And then we know that white light, the reason why white light will be able to break up is that as it enters the glass prism, with the same frequency of all these things, right? With different frequencies, that is going to affect the what? The speed. It will affect the speed of the color. While the other colors will be faster, other colors will be what? Will be slower. The fastest color will be red, and the slowest color will be violet. Red will get refracted the least because it's faster, and violet will be refracted the what? The most because it's the slowest out of all these things. Is there a way to remember it? Roy G. Beef. And then you say we are increasing frequency on the other side, and we are increasing wavelength in the other side. So grade 12, I'm just going to give you a 3-minute activity just to see if you can answer some of the questions related to the things that we have looked at. Okay, so the activity is here. The diagram below shows the reflection of a light ray that strikes a flat mirror with a 30-degree angle of incidence. Right, your 3 minutes starts now. Right, Greto, welcome back. I hope you've attempted the activity, and I hope it is as simple as I think it is. So the activity is, the diagram below shows the reflection of a light ray that strikes a flat mirror with an angle or a 30-degree angle of incidence. And the first question there that we're being asked is, what is reflection? Or more, it actually should be define reflection. So that's actually what they want from that question. They want you to define reflection if they ask what is the definition that is expected from you. Let's hope that you are getting that right, or at least you have an idea of what reflection is. Okay, and then simply indicating that the array AO, this one here, this is the incident ray. We've been saying, and all rays, incident ray are incident rays. Okay, right. And then this ray OP, this one is the one that has changed direction upon striking the interface, which is the reflected. This is the reflected ray. Everyone should be able to get that. Not even one person should get this wrong. You can clearly see this is incident ray, this is the reflected ray. What is line M? We call line M normal. It is normal here. As you can see, this is normal. And this angle that is measured from the normal to the incident ray is called the angle of incidence. okay? And this one that is measured from the normal to the reflected ray is called the angle of reflection. So that was just a simple activity that I was giving you to just check if we are moving together so far. Okay, right. Now, grade 12, let's try and look at how this refraction of light is actually helps us in our lives. Okay, how is it applied in our lives? Okay, this refraction of light passing through, right, helps us because it helps us with things like such as lenses. Okay, it helps us with things like lenses. We get to have lenses, or we get to use lenses. As I'm speaking to you right now, I'm speaking to you through a lens because there's a camera facing me that allows me to speak to you. There's a lens in that. I'm using this tablet here. There are lenses in the tablet. You are probably watching me through a phone. The phone has lenses. These things are helping us, and these things get to help us because of the refraction of light, because of the fact that light refracts. Okay, so let's go and talk about lens. The lenses that we are going to look at, we are going to look at two lenses, okay, or two types of lenses. And the first one is going to be the convex lens. And we say, even though this is not like a formal definition, as there is no definition in our exam guideline, so we just want to be able to differentiate between a convex lens and a concave lens. A convex lens is the one that is thicker in the middle than on the edges. As you can see, the edges of the convex lens are very thin. Okay, while the edges of the convex, or the middle of the convex lens is thick. So the convex is thicker in the middle and thinner at the edges. And that is enough definition for you there. Even if they say differentiate between a convex and a concave lens, you say convex is thicker in the middle and thinner in the edges. You should get your you should get your marks there. Right. A convex lens is also known as a converging lens. Okay, it is also known as a converging lens. As you can see here, it is written thin converging lens. So it can be called converging lens, or you can call it a what? A convex lens. Why is it known as a converging lens? This is because light rays, when they pass through a convex lens, they get refracted. Again, very important. Refraction helps us with these lenses. They get refracted, but the way in which they get refracted such that all of them, as if they are chasing a certain point that they are focusing on. It's as if they focus on a certain point, as these light rays get refracted in a convex lens. It's as if they are focusing on a certain point, and that point is called the what? The focal point. So all light rays that are going through the convex lens, they converge. They converge on one point. It's as if it looks as if they are converging on one point. So that tells us that this is a converging lens. All light rays there are converging. Okay, that is very important. So what we're now going to we're just going to go straight to the type of images, because lenses will create or give us images of a certain object. Okay, so we're going to look at the type of images that can be created by a convex lens. Okay, different types of images are formed through a convex lens. It forms a lot of images. It's probably the most used lens, the convex lens, as compared to the concave, because it forms different types of images, and these images will have different properties, of course. So to know that I'm going to use this convex lens because I want this type of image. Okay, so the following are the images that can be formed. Okay, it's very important that you are able to draw this grade 12. It's unfortunate that I can't draw it from you to show it from start to finish, but it's important for you to know how to draw this. Okay, what would you need to draw? You will need to ensure that you always draw this line that we call the principal axis. Okay, here there must also be another line here that is called the optical axis. This center here, as we said in the beginning of the lesson, if you remember those terminology, this center here is called the optical center. So these are the optical axis, these are the principal axis. This is optical center, and then you draw your focal points, or focal points. This is a focal point, this is a focal point, and this is double the focal point, or the focal length, double the focal length. And the focal length, that will be the distance from the optical center to the focal point. That is called the focal length, and this is just double. The length from here, the optical center, to the focal point is equal on both sides. So if this was 2 centimeters, this would be 2 centimeters as well. And double will be 4, and then the other side will also be 4. Okay, now we start forming image. If in your convex lens, the image is right on 2f, double the focal length, double the focal length, okay? Or the object, sorry, not the image, but the object here. The image will be formed exactly on 2f on the other side. That's where the image will be formed, okay? And what are the properties of that image? That image that will be formed will be real, and that image will be inverted, and you say that image has the same size or is equal to the object itself. And these properties are important because they are asked in exams. Give the properties of the image. You have to say, is the image real? Is the image inverted? Is the image the same size? And you always want to stick to those 3 properties and not confuse yourself. So how do you go about drawing all of this? Well, you will draw your object. Usually for the object, we use an arrow with an arrowhead. Okay? And then this is how you are going to draw, okay, your light rays, because these light rays will not be drawn for you. You have to draw them yourself. You draw the light ray that is parallel to the principal axis, and the light ray will move until it hits the optical axis, this vertical line, okay? And then draw the light ray such that it passes through the focal point. That should be your first light ray, okay? This one is not there yet. Okay, then next you draw the second ray, and the second ray should pass through the optical center. When you draw that ray somehow will intersect and meet with the first ray that you drew, which was the one that was parallel to the principal and going through the focal. Where the 2 rays meet, that will be the head of the object that you were drawing. I hope you understand me, grade 12. Hope you understand what I'm saying here. So you draw all your principal axes, your optical axis, you have your optical center and your focal points, okay? Then from there, you put your convex lens here, Then from there, you draw your object. The question itself will tell you how long the object should be. Let's say the object is 2 centimeters, okay? Now you draw the line parallel to the principal axis such that the line touches the optical axis. Then from there, you draw that line from where it touches the optical axis through the focal point, the first focal point, then just draw a straight line there. Then go and take the line from the head of the object again, and then run it through the optical center. Where the 2 lines meet, that will be the head of the image that will be formed by that particular convex lens. And that image that will be formed will have certain properties, okay? And the property for this particular image is that it will be real, it will be inverted, it will be what? The same size, okay? There are 5 options, okay, that we have in grade 12, okay? The one is not indicated here in my diagrams, but one could have been here. If the object was here before 2F, the image would have been formed between F and 2F. And the properties of that image would have been, it would have been a real image, it would have been inverted, but it would have been smaller than the object, okay? So, if I move my image again, remember now, I've moved it from 2F to here, okay? Now, what if I move it and I place it between 2F and F? I will draw the same things all over again, okay? The image there will be formed between F and the image there will be, the object is between F and 2F. So I'm putting the object between F and 2F here. The image will be formed beyond 2F. So it's as if the image is moving. Okay, if you move the object, the image also moves as well. And the image will be real, it will be inverted, and it will be enlarged or bigger. I hope you are seeing here this sort of a pattern. Before 2F, the image was real inverted, smaller than. At 2F, the image is real and inverted, equal to. Between 2F and F, the image is beyond 2F. So it's as if the image is running away. It is real inverted, and the image keeps on gaining size because it was smaller than, it was same size, now it is enlarged, meaning that it is bigger than the object. Okay? And then, if we continue, if we place it exactly at F, the focal point, okay, there you will see, if you do the drawings, okay, what you will notice is that the right rays will be parallel. There will be no point where they are meeting, okay? That's if the object is exactly at the focal point F, okay? Theoretically, we say that the image is formed at infinity. That's theoretical. But in practicality, there is no image. So it is enough for you, grade 12, to just say there is no image, okay? So in that case, you won't even need to stress about the properties. So in this case, no image is formed, okay? Even though theoretically it's saying the image is formed at infinity, but practically no image is going to be formed in that case, okay? And then situation number 5, if you put it between F and the optical center, between F and the optical center, the object is there now, okay? If you do the drawing, it will start looking like the image is not formed again. But what you will notice is that they won't be parallel, okay? When you see that they won't be parallel, then you can go back and produce them using dotted lines, as it has been done in this diagram here. So when you do that, the image will be formed, but now the image will not be formed on the other side, it will be formed on the same side as the object. And that image that will be formed will be erect or upright, another way that could be used. It will be erect, and erect object, it will be upright, and it's on the same side of the lens. Okay, right, and that image will not be a real image. That image will be a virtual image, and the image again will be what? Extremely enlarged. It will be extremely bigger. It will be bigger than the object. Okay, right. Okay, so some uses of a convex lens. These are some uses that you can look at: microscope, a camera lens, a projector, a flashlight, and a magnifying glass, and so on and so forth. But for most important for me is this one here. It is used, right, by people who wear eyeglasses and people that we say are what? Are hyperopic, okay, or hyperopic, or far-sighted. These people are far-sighted. They use that, it corrects, okay, because people who are far-sighted says that their natural lens converges beyond the retina. So the convex lens helps them to bring back the converging on the retina such that they can see. But what is important for you is just to know that far-sighted people use lenses, convex lenses, okay, to help them see better. Okay, and then we have the concave lens. The concave lens is a lens that is thinner in the middle than on the edges. It is also known as the diverging lens, as the light rays there are diverging. Okay, the light rays diverge, they don't converge, they move separately apart like that. Okay, so what is nice about the concave lens is that the concave will only form one type of image. So we don't have a lot of type of image that is formed by the concave. It's only one type. And that image that will be formed by the lens will always be a virtual image, and that image will always be erect, and it will always be diminished, or it will always be smaller than the object. Okay, this part here is simply just theoretical. It's just theoretical, this part, to say if the object was at infinity, okay, then the position of the image will be exactly at F, and it will be virtual, erect, and highly diminished. So small that it will be difficult to see. That's just a theoretical matter. But for practicality, this is the part I want you to focus on. To say, let's say the object is anywhere, either before 2F, between F and 2F, between F and optical center, wherever you place it here, okay, the image that you are going to form will always be virtual. The image you are going to form will always be erect. The image you are going to form will always be diminished or will always be smaller. And that's the nice thing about the concave lens. So there is nothing too much that we should speak about. As you can see here, the light rays, when you draw them such that they are what? They are diverging. So you will have the object here, and then you draw the light ray number 1, it will touch the optical axis here. And then you draw it, the line through where it touches the optical, and as if it was coming from this focal point here, and it diverges. And then you draw a line from the head through the optical center. Where they meet, that would be your what? That would be your image that is being formed then. Okay, right. Some uses again of a concave lens. You have here telescope, uses a concave lens, flashlights, uses some flashlight, uses a concave lens, and some binoculars also uses a concave lens. But the one that I want you to know the most is the use of people that have or are myopic, people who have myopia or people who are myopic. Right? People who are myopic use a concave lens to correct their issue of sight. These are the people that we are saying that are short-sighted. They are short-sighted. They see things only when they are close. And the reason why they see things only when they are close is because their natural lens on their eyes will converge before the retina. Converges before the retina. So when you put in a concave lens such as this one, it helps because it diverges the light rays before they can converge in the convex lens that is natural in their eyes. By that small diversion that happens before they reach the eye, it helps push the converging or the place where it converges such that it converges here on the retina. And then the person is able to see clearly and properly. Okay, so I hope we are getting that grade 12. Right, so let's just go through the summary of what we have looked at. We have looked at the reflection, we have looked at laws of reflection, we have looked at the refraction, and then we looked at the critical angle. And then from looking at the critical angle, that led us to look at total internal reflection. And then from there, we looked at dispersion of white light, and then the application of light itself in through concave and convex lenses, and then the transmission of light through a convex lens and a concave lens, drawing all those diagrams. Okay, so those are the most important things that you want to look at grade 12 when it comes to light, right? So this is just the homework that I want you to go through during your time. Just try to answer this question and check if you are able to answer questions relating to reflection or refraction, or even a convex lenses. If you are able to answer these questions, then you are one step closer to being ready for the examination. Okay, grade 12. This is it. Make sure you join us the following week on the 16th of May while we do electromagnetic radiation. Thank you.